Hello and welcome once again for another ES340 video. This is day 14, part A. So recall that we had the following equation for, in the case of an internally reversible process, for the change in entropy. Okay, so this can also be rewritten as delta Q internally reversible equal to TdS, which is where we got our start in the TdS equations, and we were very interested in that. So this implies that the heat transfer in an internally reversible process is equal to the integral from 1 to 2 of TdS. So we actually can take this to be, we can actually use this as a representation of the heat transfer visually. This is why the TdS plot, for instance, or the TS plot, excuse me, is very useful. In this case, I'm going to use capital S here. So if I have some state 1 and I go along some path, hopefully a smooth path, to state 2, then the area under this curve, this region right here, is my heat transfer, at least for an internally reversible process. This doesn't work for irreversible processes, but it does work for an internally reversible process. So we can actually take this area, which is the whole region under this curve, all the way down to here, to be the heat transfer in this case. Okay. Now, a thing to note is that T must, as usual, be absolute, right? Because otherwise we could get area underneath the curve here. We could get area down underneath the S equal to 0 curve here, or the T equal to 0 curve here, which would not be good, and would not help us compute the heat transfer. So we must be using an absolute temperature in this case. Now, this can be quite useful in cases where we're dealing with a variety, at least visually it's helpful. We might not be able to necessarily compute it in all cases, but if we have a nice type of cycle, then actually we could use that to help us compute these areas, to compute this internally reversible heat transfer case, which could be useful in a variety of scenarios, right? In this case, I have this possibly complicated curve for the path from 1 to 2, but in some cases, such as the Carnot cycle, the path is, at least on a TS diagram, is very simple, and has a very nice shape that you could, in principle, use to help you compute things such as, say, the thermal efficiency. So remember that the thermal efficiency is equal to the work done by the cycle divided by the heat transfer, Q in, here. So if we want a nice A nice thing about this, let's actually draw the TS diagram. This is why the TS diagram is one of the reasons it's quite useful. Just like, remember, the PV diagram was useful when we wanted to figure out how much work was done, because it's just the area inside of that curve. It's a similar kind of story here. Let's call this A and B. Suppose we have this cycle that's happening at some temperature. Let's call this the cold, and this is going to be the hot reservoir temperature. It turns out that, the Carnot cycle in this case is just a rectangle, which is really useful. And I'm gonna shade in this area. This area inside of here, so you know, the area of a rectangle, is the work done by the cycle. And then the area that goes, again, because we were doing heat transfer, the area underneath this top curve here so that shaded region all the way down is Qn. So basically we can actually use the TS diagram in this case to find that that the thermal efficiency would be the ratio of the areas of these two rectangles here that we have on the TS diagram for the Carnot cycle. Really nice. And basically you should see that this pops out with exactly what we expect. Eta ends up being, I'll let you check for yourself that this is true, but eta ends up being 1 minus Tc over Th. If you do the ratio of these two areas. Okay? Okay, so that's for an internally reversible cycle. We can actually find, so remember the Carnot cycle is a series of internally reversible processes. So I'm going to call that an internally reversible cycle because it has a series of internally reversible processes. Now, the next topic that I wanted to discuss here is the closed system entropy balance. Now, I've been kind of hinting that we were heading here, so now we are exactly where I wanted to be, which is discussing the entropy balance. And the entropy balance, we're going to treat it very similarly to the energy balance, except for now many problems that you're going to be dealing with are going to need both. The energy balance, you saw this, you should have seen this already in a group work, but the energy balance and the entropy balance are going to need to be used in coordination with each other in order to solve many of these problems. So you can't forget all of the stuff that you learned before. But the way we treat them is going to be very similar. The entropy balance, you figure out what terms stay, what terms go, and then you work out what needs to be obviously computed in this case. But this is the entropy balance equation, the whole thing here. This is my entropy production term. And recall that there was another name for this as well. It's called the strength of the irreversibilities, right? So we don't produce entropy if there are no irreversibilities, okay? So if there are if it's reversible, then we don't produce entropy. But otherwise, we produce entropy. And that's true in a closed system. It's also true in an isolated system, actually. And this term is the entropy transfer term. And obviously this is the change in entropy. So notice that in order to have entropy transfer, we need to have heat transfer. If there's no heat transfer, then we can't have entropy transfer. Now I want you to think about what the equation, I want you to think about what type of system this is. If it's a closed system and there's no heat transfer, you definitely should think about that. But if there's no heat transfer, then obviously we get a change in entropy that's just equal to the entropy production term. If there's no entropy production, then we get, which would mean that the system is reversible, then the only way that the entropy can change is through entropy transfer, okay? Now an interesting thing, and I know that this kind of messes with people's heads, we know that delta S has to be greater than or equal to 0 in an isolated system. However, because I've seen people get this messed up all the time, delta S can be less than 0, so negative, in a closed system. That's also true in a closed system or a control volume as well. So the trick here is that an isolated system has to have an increase or have the entropy stay the same at the very least, but it has to have an increase in entropy. But a closed system can have this heat transfer, which could be negative, right? It could overwhelm the entropy production. But the basic idea in that case is that if I account for the surroundings as well, because the surroundings we're not counting them as part of the system in a closed system. If the surroundings are taken into account, then the system plus the surroundings would have to have a positive change in entropy, non-negative basically, because you could have a reversible system, but most of the time we're not going to be dealing with simply just reversible systems. We'll have something that has some irreversibilities. So in that case, the entropy of the system plus its environment, if you zoom out far enough to include everything, the entropy would have to increase. Okay? So I want you to think of, like, for instance, as far as we know, the universe is an isolated system, right? If I zoom all the way out to the entire universe, as far as we know, there's no input of energy from something outside of the universe, right? So as far as we know, the universe itself is an isolated system. Therefore, the entropy has to always be increasing, okay, in that case. So if I zoom in on some small system, I can have a negative entropy change, but the entropy change of the system plus its environment, so plus the entire universe, has to be greater than 0. Okay. So now the question becomes, you should immediately be thinking, okay, yeah, I once I get into a control volume, I'm going to have yet another equation, and that is actually true. The entropy rate balance equation, right? So for a control volume. So this is the entropy balance equation up here. Now we have the entropy rate balance equation. And this is going to be the sum over all of the heat flow terms divided by the temperature of the reservoir that heat flow is coming from, plus the entropy production rate. So this is going to be the entropy production rate. This will be the entropy transfer rate. And this is the rate of change of entropy. Okay, so this would be my entropy rate balance equation. And again, you will be dealing with example problems, which I'll have a few example problems here, but you'll be dealing with example problems dealing with when I can drop some of the, one of these terms, or obviously if I can drop both of them, it's just a nice reversible system, but because the change in entropy is just equal to 0 in that case, very boring. But if I can drop one or the other terms, that'll be the interesting scenario. Just like the energy balance equation, which terms can I drop in the energy balance equation was kind of the key thing. And similarly, in the entropy balance equation, which terms can I drop here? Or do I have to leave them all, right? That could be a scenario. So that's all I'm going to cover in this video. I just want to have two quick clicker questions. So the first one is, for a closed system, the change in entropy when there is no heat transfer is given by which of the following equations? So if there's no heat transfer, which of the following equations would be the energy balance, or the entropy balance equation in that scenario? Okay, delta S is equal to these two terms, just this term, or none of those. Okay, and the next one, clicker question 2, given what you know about sigma, which is the entropy production term, and the above equation, whatever you get for the equation above, in a closed system with no heat transfer, what must be true of delta S? Which of the following must be true? Is delta S, in that case, think about what kind of system that is, by the way, if there's no heat transfer and it's a closed system. What must be true of the change in entropy? That it's less than or equal to 0, greater than or equal to 0, equal to 0, or none of the above. See you again in the next video.